Hi, and welcome back. This is lecture 3 of 3 on chapter 10. Now, chapter 10 introduces us to rotational motion. Um, so far, we've talked about the basics of rotational motion, and through the introduction of rotational kinetic energy, we saw our first real new concept, which was the moment of inertia. Now, today I'm going to start with another new concept. It is the rotational analog to force called torque. So, that said, in order to understand torque, what I'd like you to do is to think about using a wrench on a nut. So here's your nut. Here's the bolt that it's threaded on, and then here is the wrench. It looks something like this. Now, so there are certain ways I could exert a force on this wrench to get it to rotate. For example, if I exerted a force straight down the handle of the wrench, we know nothing would happen. So if I push through the center, nothing happens. Likewise, if I were to pull this way with the wrench, I'm not going to get any sort of rotational effect. So ideally, what I would like to happen to get this thing to rotate, and we'll say we want it to rotate this way, is to have some part of my force be in this direction right here. Forces that are in this direction are going to cause the rotation because they're tangent to the circle this handle would make. Now, that said, let's take this wrench right here and sort of mimic it the following way. This right here is going to be the distance from the point of rotation to where we're applying our force to get this thing to rotate. And let's suppose that this is the force that I'm going to exert. So, this is my point of rotation, which I'm going to call P. I'm going to call this R. R is the distance from the point of rotation to where I'm applying the force. This is my force F. And what I'm going to do is to extend R this way. Now, actually, let me keep that there. What we want is this part of the force right here. It's this part of the force that's responsible for making this thing rotate. So you think about breaking up into components. You have a component that's along the handle, and as we saw, exerting forces along the handle don't cause any rotation at all. And then you have the component that is perpendicular to or orthogonal to R. This is the part. And if you think of this as being the angle between the direction that R points and the direction that F points, this would be the sine part. So F sine theta is what causes the rotation. Now we're going to introduce the action of R here in a second. And the way I'd like to introduce that is I want you guys to think of a door. So here's a door. We know doors have handles. This one will be round, we'll say. And plus, doors have hinges. So there's a hinge over here, maybe here, maybe here, and maybe here. Now, if I were to pull this door open or push this door shut, we'll just use pushing the door shut as a good example. I reach, pull on the handle, the door opens, or push the handle, the door shuts. Now, that said, there's a reason why the handle sits way out over here. And you can actually try this experiment at home. If you open your door, we'll say to your bedroom or something like that, and you push where the handle is to shut it, you'll notice that it's really easy to get it to shut. Next, open your door and push at the halfway point between the handle and the hinge. You'll notice that it's actually a little bit harder to get the door to shut than it would be if you pushed it out over here. what you'll notice as you continue to do this experiment and push closer and closer to the hinges is that it takes more and more and more force to get the rotation to occur. And if you were to actually push at the hinge on this axis, this is the axis of rotation of the door. If you were to push there, the door wouldn't do anything. Okay? So what that means is that as you get further and further and further away from the point of rotation, the force that you apply causes that rotation to occur in an easier manner, if you want to think of it like that. So if you actually do the math, what you'll discover is that there is a linear relationship between how easy it is to get this thing to change its rotation, the force, and how far away the force is applied. Now, that combination of stuff is called torque. We abbreviate torque, or at least we denote torque, with the Greek letter tau. It is R cross F. Or in magnitude, torque is R F sine of theta. So here's your sine of theta term that causes the rotation. So this causes the rotation, and this is where the force is applied. As you can see, it's a linear relationship. Okay. Now, that said, torque is a really good example of using the right-hand rule. This is a good place where you should consider using the right-hand rule. Now, if you were to push your fingers in the direction of R here, and then close them towards your palm, let your palm face in the direction of F, what you would notice is that your thumb would point up. Okay, so up means rotation that changes in this direction right here. Now, if you think about a vector as being an arrow with, we'll say, a tail, kind of like an actual literal arrow, okay? If you look at the tip of an arrow, you see the point. So one way you can denote a vector coming out of the page, which in this direction, using the cross product of the right-hand rule, would give your thumb pointing out of the page, is with a circle and a dot in the center. Now, let's pretend that the force was this way. This force would cause rotation this way. If you use the right-hand rule in that case, your thumb would be into the page. And if you think again about a vector as being an arrow, looking at the tail feathers, you see that. So this is out of the page, and this is in. Okay? Now, so that said, let's do a few examples with torque. We have a wrench of length 15 centimeters is used to tighten a nut. If 250 newtons of force is applied at the end of the wrench at the most efficient angle possible, what torque does the nut feel? If a cheater bar that extends the length of the wrench to 75 centimeters is used, what torque is generated? So again, if you think about a nut here with a wrench like that, the distance from the center of the nut to the end of the wrench is 15 centimeters. Now, here it says we want to apply 250 newtons of force in the most efficient angle possible. So if you think of this as being R, the F that we would want to use would be the angle, or at least the F that gives us the angle in which all of the force does the rotating. So you want that to be 90 degrees. Okay, so here's the direction of RF. So if we want this thing to rotate in the most efficient way possible, you push out at the end of the handle and you push it 90 degrees to R. Okay, so what are we given here? The length of R is 15 centimeters, which is 0.15 meters. And the force that we're applying in magnitude is 250 newtons. Now, the magnitude of the torque is R, F, sine of theta. But the angle here is 90 degrees, and sine of 90 is 1, which means that it's just the magnitude of R times the magnitude of F, which in this case would be 250 newtons times 0.15 meters. Now, if you do the math here, it's 250 times 0.15, or 37 and a half. 37 and a half Newton meters. Now, you may recognize Newton meters as something that we've seen before. Specifically, work is force times distance, at least if you want to think of it in terms of constant forces. Okay? And in this case, it would be a Newton meter. This is not a joule. Okay? So I know work is measured in joules, which is a Newton meter. We do not call these joules. This is not energy. Okay? Now, what about the direction? Well, if you put your fingers along the direction of R, which would be this way, and you face your palm in the direction of F, that gives you your thumb pointing out of the page. Now, out of the page means counterclockwise rotation. That is positive torque. So my torque here would be 37.5 Newton meters out of the page. That would be the vector. Now, if you wanted to think of this in terms of a three-dimensional coordinate system, this being z, we'll say this being y, and this being x. Then, if I keep my force in my r in the xy plane, here you get counterclockwise rotation this way. That would be up. That would be the direction of your torque. So you could also say that if you drew your picture this way, that your torque as a vector was 37.5 Newton meters in the z-hat direction. Okay. Now, the next part says we're going to use a cheater bar that extends the length of the wrench to 75 centimeters. Now, cheater bars are really just hollow tubes. And what hollow tubes do are to give you a way to push further out. Now, what that does is to allow you to generate more torque, but you have to be careful if you're doing some sort of wrenching on something, because if you generate too much torque, you can actually shear the bolt and cause it to break, or you can break your wrench. Okay? So cheater bars are necessary, unfortunately, but they have a tendency to break wrenches if you're not careful. So in this situation, the only thing that's changing is where we're applying the force, where R is. In this case, R would be 0.75 meters, or 75 centimeters. So the torque in this case would be 250 newtons times 0.75 meters. And if you do the math in this case, it is 250 times 0.75, 187 and a half. The direction being out of the page. Okay. Now, so as you can see, if we just use the wrench itself, it's 37 and a half Newton meters. If we add a cheater bar into the mix, by extending the length of the handle, we've generated substantially more torque. Now, it's because of this. It's because when you take and what you're doing here is you're changing the rotational motion. You're starting from rest and you're causing basically it to accelerate like this. So that's the reason why we say torque is the rotational analog of force. It causes angular acceleration. Okay? Now, that said, let's do another example. Two kids sit stationary on a level seesaw. Kid 1 has a mass of 35 kilograms and sits 1.5 meters away from the pivot point. If Kid 2 has a mass of 45 kilograms, where does she sit? Now, so I want you to think of a seesaw like this. Here's my pivot right here. at the center, like that. Now, we're going to put kid 1 down over here. Here's kid 1. Obviously, this is not drawn to scale. And the distance that kid 1 is away from the pivot. This is the pivot point right here. This is what the seesaw can tilt around. The distance here, I'm going to call R1. And R1 is 1.5 meters. Now, the mass of the first kid is 35 kilograms. Now, kid 2 is going to sit somewhere over here. We know their mass. Their mass is 45 kilograms. The question is how far away from the pivot point do we have to place the second kid in order to get this thing to remain stationary? So we're looking for R2. Now, torque, like I said, is the rotational analog of force. And you can sum torques up just like you can sum forces up. But when you sum a torque up, when you sum your torques up, you sum them about a point of rotation. It could be this. We could, if we wanted, sum our torques over here because, it could potentially rotate here or could potentially rotate here or rotate here. We're going to be seeing that later on when we do some statics problems dealing with this. But this is our point of rotation right here. So if I were to draw a picture with this being the vector R1 along the seesaw, and this is my pivot point right here at P, and this being the weight of the kid, since this is a level seesaw, we know if it's level, the angle between this kid's weight and R1 is going to be 90 degrees. Okay. Now let's take a look over here at kid 2. Here's another R like this. This is R2. And this is FG2. Again, level means 90 degrees. So we have two torques at work. We have kid 1's weight wanting this thing to rotate this way. So kid 1's weight wants it to rotate counterclockwise. So torque 1, we can see, is going to be counterclockwise. On the other hand, kid 2, his weight, or her weight rather, makes her to want to rotate this way. That's clockwise. So if you think of in or out of the page, if you were to take and put your fingers in the direction of R1 and let your palm face towards kid 1's weight, when you take and you close your fingers, your thumb points up. So torque 1, which is counterclockwise, is out of the page. That's positive. That would add in as a positive torque. On the other hand, kid 2, her weight makes it want to rotate clockwise. And if you take and you put your fingers in the direction of R2 and then let your palm face in the direction of kid 2's weight and then close your fingers, your thumb will point into the page. So kid 2's torque is in. That adds in as a negative. If I add up the torques that I have here, I get 0 because it is stationary and is not experiencing any change in rotation. Forces cause changes in velocity. Okay? Torques cause changes in rotational velocity or rotational acceleration. So what we have here are two torques, torque 1 and torque 2. They add to 0. Here, torque 1 adds in as a positive. Torque 2 adds in as a negative. Now let's talk about what the torques look like. Torque 1 is going to be R1, F1, or FG1 rather. sine of the angle in between. And the angle in between here is 90 degrees. So this is 1. So it's just R1 times FG1. Torque 2, R2 FG2. Sine of theta. Again, 90 degrees, so that's 1. So this is just R2 FG2. So you add the torque sub. R1 FG1 minus R2 FG2 is equal to 0. Now FG1 is the first kid's weight. That's just M1 times G. FG2, the second kid's weight. M2 times G. So R1 M1G minus R2 M2G is equal to 0. G's cancel. We're trying to find R2. If you solve for R2, it's going to be M1 divided by M2 times R1. And if you take and you put the stuff in, M1, 35 kilograms, R1, 1.5 meters, M2, 45 kilograms. So if you do the math here, you get 35 times 1.5 divided by 45, 1.17. 1.17 meters. That's where our second kid would need to be in order to keep this thing level. And if you've played on a seesaw before, you know that's how it works. The one who weighs the most has to get closest to the pivot in order to make things balance. Okay? Now, that said, torque, like I said, is rotational force. And let's not forget that you can write it as R cross F. Now, for the moment, I would like to think of a situation in which the angle between R and F is 90 degrees, and I just want to look at the magnitude of the torque. In that case, RF sine theta would just equal to R times F. But what's F? Well, in magnitude, F is m times a. Acceleration, we know, when it comes to rotational motion, is r times alpha. Because let's think about this. If you push on something with a force like this, and that something is stuck at one end and pivots around, then what you do is you cause the acceleration to be in a tangential direction, right? So this is tangential acceleration. So here, the torque is R times M times R times alpha, or M times R squared times alpha. Now you may notice, or you may have seen mr squared before. If you think about this being a mass that we're pushing on at this point, this being r, this is the point of rotation. This is the moment of inertia. Okay, this is I. And now it should be all that surprising to say that torque would be I times alpha. And the reason why it wouldn't be all that surprising is because I is the thing that acts like mass, and alpha is the thing that acts like acceleration, and torque is the thing that acts like force. So it looks the same. Even though as a concept it's new, it's really not all that new. So this almost completes our entire list of rotational to translational analogies. The only new idea is that of I. Okay? So, two ways that you can write torque: as R cross F or as I times alpha. Okay. Now, likewise, you can sum up the forces, or not the forces, rather. You can sum up the torques, rather, to get the net torque. That is, all of the torques that are acting on something combine to produce a net torque, which you can write as I times alpha. This looks really familiar. This almost looks like what you do when you sum up the forces to get the net force, which is m times a. Oh, this is Newton's second law. Newton's second law of forces, Newton's second law of torque. Okay, so same idea, except the torques that we are going to deal with are going to primarily be in or out of the page. So you're not going to be stuck dealing with complicated things like having to break a torque up into an X part, a Y part, and a Z part. All you have to do is ask the question, is it rotating clockwise? Is it rotating counterclockwise? So this will be the first example that we work where we have an object with a well-defined moment of inertia that's experiencing a change of motion due to a torque. So here we have a force of 115 newtons that's applied to the edge of a cylinder. And what you're looking at here is the cylinder straight down its axis. So it's rotating about the long axis, basically. The angle here between the force and the surface is 25 degrees. We know the cylinder's mass is 1.25 kilograms, and it has a radius of 15 centimeters. And what I want to find is the angular velocity after 5 seconds. And we're going to assume that it starts from rest. So what we're given here is a force whose magnitude is 115 newtons. We're given the angle of the push, which is 25 degrees. We're also given the mass of the cylinder, 1.25 kilograms. Its radius is 15.0 centimeters, or 0.150 meters. And we know we're looking forward 5 seconds. Likewise, the initial angular velocity is 0. Now, what we're trying to find is its angular velocity after 5 seconds. So, that said, we know this is a cylinder, and we can look up the moment of inertia of a cylinder. And let me get that real quick. We want the cylinder down a long axis. So let's see here. That is going to be 1/2 mr squared. So we know I for the cylinder is 1/2 mr squared. Now, so the best way to start with these things, at least in my opinion, is to start with the rotational equivalent of a free body diagram. So really what we want to do is draw sort of like a force diagram, except instead of having our object at the center, what I'm going to do is to put the pivot point at the center. So that would be the center of the cylinder. And if you look here, this will say is our R. going from the center of rotation or the point of rotation to the point on the cylinder where the force is being applied. And this would be the force right here. Now, we know, because of the way the problem's set up, that the angle right here is 25 degrees. But when it comes to looking at torque, we don't want that angle. We want the angle between the force and R, which would be this right here. All right. So again, let's just label stuff. This is R, this is F, and this angle right here, I'm going to call alpha. So if this is 90 degrees total, and this part is 25, then this part right here should be 65. So alpha, which is the angle between F and R, is 65 degrees. Now, so what that means is that we can find the torque. First thing we'll notice here is that this force is going to cause this to go counterclockwise, which means it's going to be positive torque. So positive torque means positive acceleration. It works just like Newton's second law. Okay. So we also know that in terms of the magnitude of the torque, it's going to be the magnitude of R times the force times sine of the angle in between, which is going to be alpha. Okay, actually, I'll tell you what. Since we've already reserved alpha for angular acceleration, and we're going to be using that, let me call that something other than alpha. It makes me feel a little weird there. So I'm going to call it beta. That's something that we haven't used before. So there's a beta. This is beta. And this is beta. This is just for consistency. So now this torque right here is going to act on the inertia of the cylinder and cause it to experience angular acceleration. All right. Now, so if you sum up your torques using Newton's second law for torque, you want to write sum of F. We do it so much, right? So we sum up our torques to get the net torque. We only have one, and that's this one right here, which is positive because it's going counterclockwise. So our torque here is going to be, I'll call it just tau, okay? And we know it's R times F times sine of beta. This we know we can write as I times alpha. It's the cylinder that's experiencing the torque, and as a consequence, it's going to get angular acceleration. So it works just like Newton's second law. Okay? So now what's the moment of inertia of the cylinder? Well, it's 1/2 mr squared. So RF sine of beta is equal to 1/2 m times r squared times alpha. So we're going to lose one r right there. Okay? And our angular acceleration here is going to be 2 times f sine of beta divided by mr. Okay? So now we can find our angular acceleration. It's just a number because we know everything here on the right-hand side. And given that, what we have is a simple rotational kinematics problem. We'll just write down our three kinematics equations, and then from there, given our initial velocity of 0, we can very easily find the angular velocity after 5 seconds. But let's go ahead and find out what alpha is to begin with. So that's 2 times 115 newtons times sine of 65 degrees divided by 1.25 kilograms times 0.150 meters. Now, if I put this in my calculator, let's see, 2 times 115 times sine of 65, and then I have to divide that by 1.25 times 0.15. I get an angular acceleration of 1,111, actually 1,112 radians per second squared. Okay? Now, so given all that, next, what we're going to do is to write down our three kinematic equations. We have omega is equal to omega naught plus alpha times t. We have theta is equal to theta naught plus 1/2 alpha t squared plus omega naught times t. And then we have omega squared minus omega naught squared is equal to 2 times alpha times theta minus theta naught. Okay? Now, let's not lose sight for what we're trying to find. We're trying to find omega. We're given t, we're given an initial velocity of 0, so if we go ahead and plug that in, that gets rid of a couple of terms. We're going to assume our starting angle also is 0 degrees, which or 0 radians, which really isn't going to affect what we're trying to do, because at the end of the day, we're going to be using this equation right here. So omega is equal to alpha times t. Alpha is 1,112 radians per second squared, and t is 5 seconds. So when you do this, you get, keeping two sig figs, 5,600 radians per second. Okay? And there's your answer. Now, so in my experience, in execution, the problems aren't too difficult. But what you have to do is to sort of get over the conceptual hump. Okay, you have to see it. So the best place to start is with this equation right here when it comes to understanding, the conceptual hump that you sort of have to jump over. This is just Newton's second law. Okay, so now remember, our force isn't applied to the whole object. Our force is being applied to a point on the object, and as a consequence, that can cause rotation. Okay? Now let's do another example. Here we have a bucket that is filled with water, and it goes around a shaft in a well, and the shaft has a handle attached to it. Okay? So we know the mass of the bucket is 15 kilograms with the water in it, and we're going to assume that the rope is massless. We know we have a cylinder with a mass. We know its radius. And we also know that there's a handle that's attached to it that's massless that has a length of 15 centimeters. So what we're going to do is to apply a force on here to hold this bucket stationary above the water. And the question is how much force do we have to apply? Okay, so in a situation like this, it's good to use not only a force diagram, but also a torque diagram. But before we get there, let's just write down the things that we're given. Okay, so we have a bucket, which I'm going to call its mass m sub b. So let's just go ahead and sort of write this stuff. Mass of the bucket, mass of this is a cylinder, mass of the cylinder. Okay, so this from the center of the cylinder out to where you would hold the handle, this distance right here. It's not the best thing in the world, but it'll have to do. So this distance right here is 15 centimeters. So that's the length of the handle. I'm going to call that R sub H. Okay. Now, we also have the the actual radius of our wooden cylinder here, which I'll call R sub C. And R sub C is 6 centimeters. Okay. Now, we know, like I said, the mass of this. I'll just go ahead and put the numbers in, since we're putting the numbers in everywhere else. This is 15 kilograms. And we know that we're holding this thing. And what that means is that when we add up the torques on this and we add up the forces on this, we're going to get 0 in both cases. Okay. So let me sort of relocate this, what we were doing here. So the mass of the bucket is 15 kilograms. The mass of the cylinder is 1.2 kilograms. The radius of the handle, or the length of the handle, is 15 centimeters, which is 0.15 meters rather. We know the radius of the cylinder, which is 6 centimeters, or 0.06 meters. Okay. And I think that is it. Yeah, that's all the information that we have. So we're trying to find the force that we're going to apply on the handle. And I'm going to assume that the force that's being applied here is being applied straight across and not at some weird angle. So the angle between R and F should be 90 degrees. So I guess you could say, what is the least amount of force required to keep the bucket and the rope stationary? Okay. So let's talk torque diagrams to begin with. You have your cylinder, which I'm going to place in the center of this on edge. Let me relocate this real quick. Like that. So there's our cylinder. Now, as drawn, we'll say on this side of the cylinder, this is where the bucket is. So the bucket is exerting force downwards due to the tension of the rope. And we're going to get to that here in a second. Now, likewise, we have the handle, which goes up over here. And we're going to exert a force on the handle like this. Now, the rope here, from the point of rotation to the edge of the cylinder, is located there. All right. So if I were to sort of fill these things in, this would be the tension in the rope. This is what this is right here. This right here would be R sub C vector. That is where the force is being applied due to the tension. This right here would be R sub H vector. This is where the handle ties into the center of the cylinder right there. And this would be the force that I'm exerting on the handle. This is what we're trying to find. And as drawn, all these are at right angles to each other, which makes the math pretty easy, or at least it makes it a lot easier than what it could be. But really what we have here are two torques. We have the torque of the push that's making this thing want to go clockwise, which would be a negative torque. So this one right here, if you do R cross F, this one right here is going to be into the page. This one right here is causing the cylinder to want to unravel, which is counterclockwise motion. And if you do the right hand roll on this, this is out of the page in torque. Okay? So two torques, and both of these torques are acting on the cylinder. Okay? So that said, we're going to draw a force diagram now. We're going to do that on the bucket. Because on the bucket, which is hanging stationary, we have a tension in the rope going upwards, and then we have the weight of the bucket going down. So the force due to gravity, I'm just going to call it F sub G, is down, the tension is up. But since it's hanging stationary, we know that when we sum up the forces here, we're going to get 0. So in this particular case, we expect to sum up the torques. Okay. And since it's being held at rest, the sum of the torque should equal to 0. In this particular case, when we sum up the forces, the sum of the forces should equal to 0. So these two conditions, plus it being at rest, is what you would officially call being in static equilibrium. But there's a whole chapter dedicated to that, which we'll be talking about shortly. Okay. Now, we also know that we're looking at a cylinder on edge, which, we dealt with right here. This is the moment of inertia of the cylinder. If we need it, we may not need it. In fact, we generally won't need it in this particular thing because things are at rest. All right. So, that said, let's start by summing up the torques. So, your first torque, which I'm going to call torque sub cylinder. Okay. This is this one right here. As you can tell, it's out of the page, so it's positive. And it is going to be R sub C times T times sine of the angle in between, which is 90 degrees, which is 1. Now, this one right here, which I'm going to call torque sub H for at the handle. This one is negative when we add it in. Okay? And if you look, it's R sub H times F sub H times sine of the angle in between, which again is 90 degrees. So that's 1. So when we sum up the torques here, R sub C T minus R sub H F sub H, we expect to get 0. This is the sum of the torques. Okay, as vectors, because it's just along one dimension. Now, when we sum up the force, once again, we expect to get 0. We have two forces. We have a tension and we have weight. Nothing interesting in the x direction. In the y direction, though, we have a tension that's positive and we have a weight that's negative. So what this does is to tell us that our tension is just the weight, which is what we expect because of experience. And this we can plug into this. So if I take my equation here for torque, I have R sub C times T. T is just mg. Now, which m is this? This is the mass of the bucket. So I should be specific about that. Sorry. M sub B. M sub B. Okay. Minus R sub H times F sub H. Okay. And this is equal to 0. So we're trying to find F sub H. That's all you're solving for. So if I move this to the other side and then divide through by RH, I get this. So R sub C, 0.06 meters. The mass of the bucket, 15 kilograms. 9.8 meters per second squared is G. And then the handle is 15 centimeters. So when you do this, you get times 9.8 divided by 0.15. 58.8 newtons. And if you look at sig figs, we have 2, we have 2, we have 2, we have 2, or actually we have 1 there. So this is about 60 newtons. So there you go. There's your force. So again, not too bad. But as I mentioned before, this is a pretty dense chapter. So, we're building on the tool set. And because there's so much similarity, it's easy to take a lot of that for granted and just kind of assume that you already know how to do the problem. But as you can see now, we have 2 diagrams that we can draw, and that's going to take practice. So you're going to have to do problems. All right, so what I want to talk about next is work and torque. So I want you to think about, let me just draw a little thing here, coordinate system. I want you to think about a mass, we'll say, going around in a circle. All right, and there's torque acting on it to make it do its thing. So let me draw a full coordinate system here. And then what I'm going to do is to sort of draw us a little circle that is going around like that. Put it here in the center like this. So here is your object. There is a force that's acting on the object. And if you were to look straight down on it like this, your force might look something like this. So here's R showing us where the object is, and then maybe here's the force off like that. Now, so we know from a work standpoint that work is what you get when you look at how that force acts over a length. Now here it's going to act along the arc, or at least the part that's going to cause a change in motion along the arc is going to be this part right here. Okay, so what we're looking for if you think of that direction right there as being the direction of ds vector, would be the dot product between these two right here. Now I called that theta. Let me call that something else. We're going to call that, again, we'll go with beta just to be different. Okay, so here, if you were to actually look at the work, that would be done, it would be the magnitude of F, which I'm just going to call F, times cosine of beta times ds. Okay. Now, so that said, we know that ds along the arc of the circle, if r is constant in magnitude, looks like r times d theta. Okay. Now, so let me shove this in here real quick. And now what I'd like to do is to talk about what this is. Now remember, torque causes angular acceleration, right? And if you remember, when we were looking at torque itself, its definition, you have your point of rotation, which would be right here for this. You have R, which would be this right here. And then you have your force right here. And by looking at this angle right here, this is the angle between R and F. By taking the sine part, what that does is to give you this part right here. The part that would be in this direction. The part that actually causes the angular acceleration. But look, over here, what we're looking at instead is this angle right here. And when you do that, instead of this being the sine part, this would be the cosine part. So what that means is that if you think of torque as being in magnitude r times f times, we'll say sine of the angle in between. Another way of thinking about it would be r times, if you knew what this was, the dot product between f and that. Now we do. In this case, it's ds because it's along the arc of the circle. So what that means is this really is just torque. This is the bit of the force that's causing the rotational motion, or the rotational change in motion, rather. And this is r. R times the bit that causes the angular acceleration. Now, so that said, you write it this way over here. What we want to do is we want to express this in terms of a vector. So let me just point out that that's torque times d theta. Okay, now let's talk about what this is. So d theta is the direction of the change in your angle. So if I were to say draw another circle, and this again, same situation, and look at the change in angle that something would experience while it's actively undergoing torque. It's about like that, I think. Whoops, actually I want to keep that. We should go to dots. This would be my initial angle, we'll say. This is my final angle right here. And to get from this angle to this angle, this would be the direction of d theta. Okay, so this is the direction of d theta vector, we'll say. All right. Now, so your torque, we know, when you use the right-hand rule in a situation like this, like for example, you do r cross f, that's going to give you a vector that is at, 90 degrees to that. So, your torque, for example, may be off like this somewhere. Okay. And d theta might be, sort of transposing this to over here, like this. So what we want is the part of the torque that actually is engaged in causing this change. So your torque is like this, d theta might be like this along the arc, and we would want whatever this is, this part, the part that transposes down onto that, which would be a dot. That's a dot product. Okay, so if this is torque and this is d theta, then the part of the torque that actually does what we want it to do would be tau dot d theta vector. And this right here is angular work. So we'll just denote it as w sub theta. It is the work integral that looks like this right here. All right. Or again, you can write it this way. Now, so let's do something with it. We have an advanced civilization that uses the rotational energy from a neutron star to power itself. Now, the neutron star has a radius of 10 kilometers and a mass of about 1.4 times that of the sun. The civilization itself uses 1.90 times 10 to the 15 watts of power. Okay, so what we want to know is how much torque would the star apply to the equipment drawing the power. So it's that torque that's being used to generate the energy. If this were applied for 100 years, by how much would the star's rotation speed change? We know the mass of the sun, And we know how many times this thing rotates. It's rotating once per second, so that's the angular velocity. So what I'm going to do is to think about looking down overhead at this star as it rotates. Stars, because of gravity, are spherical. In fact, recent experiments on the sun actually show that it is as close to a sphere as you can get, at least by our ability to measure. And that is absolutely true for a neutron star. See, a neutron star is made out of the densest material that we're aware of in nature. It's called neutronium. 2 cups of it has the same mass as about 88 Empire State Buildings, so it's incredibly dense. Now, we know the radius of our star. It is 10 kilometers. I'll put some givens up here. We know the mass of it. It is 1.4 solar masses, which if you multiply that by 1.988 times 10 to the 30th kilograms, you get something like 2.783 times 10 to the 30th kilograms. That's the mass of your star. We also know its initial rotational velocity, its angular velocity, is 1 rotation every second. Okay, so what that means is that it goes 2 pi radians every second. All right. Now, we also know the amount of power that our civilization draws. 1.90 times 10 to the 15th watts. All right. We're also interested in finding out how much of a change in speed you would see if we did this for 100 years. Now, 100 years is, get this right here, about 3.153 times 10 to the, let's see, 3, 6, 9, 10 to the 9th seconds. Right? And I think that's about what we have. Oh, yeah. Let's go ahead and convert this radius here. This is going to be that many meters, but it's going to have 3 sig figs on the inside. So it'd be 1.00 times 10 to the 4th meters. What are we trying to find? Well, first thing we want to find is how much torque is the star going to apply to this thing. So we want to find the torque. We also need to find the amount of time, or at least the change in angular velocity, rather, in that amount of time. So we want to find omega. So we're going to assume that whatever our device is as this thing rotates, we'll say it's rotating, well, I don't know, rotating this way. So this will be the direction of our angular velocity is positive. And to draw energy from it, what we want to do is to take its rotational motion. So we're going to exert our force on this thing this way. Okay, so that's our force. It's going to be that way. Now, we also know that as this thing rotates, it has a moment of inertia of a sphere. Now, we can look that up, and in fact, if you do, you get a moment of inertia that looks like, I'm going to go over here, I want to say it's 3/5 mr squared, but I just want to make sure. Scroll in, here we go. Yep, it's a solid sphere about any diameter is 2/5. There we go. So we also have, we know, an I for a sphere of 2/5 mr squared. All right, so here's what we know. We have power. Power, we know, is work over time. All right. Now, if this thing is generating, or it needs to produce 1.90 times 10 to the 15 watts of power, what that means is it needs to produce 1.90 times 10 to the 15th joules of energy for every second. So the work that we're looking at in 1 second, basically, would be 1.90 times 10 to the 15th watts generated every second. Okay, so that would be 1.90 times 10 to the 15th joules. That's how much energy needs to be produced in 1 second. All right, so I'm going to call delta T sub W right here just 1 second to keep track of that. All right. So, but we know work here is also caused by torque, right? And we know torque is, at least as a vector, is R cross F, or it could be written as I times alpha. Now we're going to assume whatever torque is being applied here, that torque is in an ideal direction. Okay, so the angle here that we'd be dealing with would be 90 degrees, so the maximum amount of energy is being generated. All right, so here it's equal to I alpha. If I look here, I is a constant. All right, it's 2/5 mr squared. That comes out. We have alpha dot d theta. And in a perfect alignment, alpha, which is slowing things down, is in this direction. And d theta is in this direction. Okay. So when we do this dot product, we're going to get a negative, which is what we want because we want the energy to come away from the rotation. So we're doing negative work here. So we're going to assume that the acceleration that's being produced is constant just to make our life easy. So when you do this, you get alpha times delta theta. All right. Now take a look here. This thing rotates once every second. All right. That's this initial rotational speed, we'll say. So what that means is that I know a relationship between omega, delta theta, and the amount of time, at least right now, in this 1 second that I'm doing work. Okay, so the work that's being done here is this much right here. This is equal to minus I times alpha times omega delta T sub W. Okay, so here I can find the angular acceleration that this thing would experience while I'm doing work over this small amount of time. And if we solve for that and note the fact that work we know is negative, then this is just a positive because it's going to be a negative times negative on one side, negative on the other side. So, whoops, our angular acceleration here is going to be the amount of work that's done divided by I omega delta T sub W. But look, work over time, this is T sub W, that's power. So it's power over I times omega. Okay? So the power that we have is 1.90 times 10 to the 15th watts. Our moment of inertia is 2/5 mr squared. The mass is 2.783 times 10 to the 30th kilograms. R squared. R is 10,000 meters. Got to square that. So that's I. And then we have omega. Omega is 2 pi radians per second. Now, all this is, again, operating under the assumption that there is no real appreciable acceleration that's being, or not, no appreciable change in velocity that's happening because of the mass of this thing, which is reasonable. So there's that divided by 2/5 times 2.783 times 10 to the 30th times 10,000 squared times 2 pi radians per second. I get an angular acceleration that's incredibly small, 2.716 times 10 to the minus 24th radians per second squared. Okay, so this is going to be the change that we would see. Now, we can also use this now to determine what the torque is. Okay. Or we could have used, well, no. Yeah, we could have used delta theta as well to determine what the torque is. So we know, here basically work is going to equal to, for this constant torque times delta theta, right? And we know that delta theta here is omega times delta t sub w. So the torque here, if you solve for it, you move this over here and you know that that's power, it's just going to be power over the angular velocity. Okay. So our power here is, again, 1.90 times 10 to the 15th watts. And our angular velocity is 2 pi radians per second. So if you do that, I get 3.02 times 10 to the 14th Newton meters. So there's my torque. So that answers that. And now we have our angular acceleration, and we can use that to find the change in omega over 100 years, right? So here's what we got. I would probably use omega is equal to omega naught plus alpha times t, noting the fact that my alpha here really is negative because it's going this way. It's clockwise. My initial angular speed is 2 pi radians per second. My alpha here is minus 2.716 times 10 to the minus 24th radians per second squared. And the elapsed time is 3.153 times 10 to the 9th seconds. So if I do this, it's going to be a ridiculously small amount of time. And it may be so small that for all intents and purposes is not measurable. But we're going to see. That's what makes these things fun. .153 10 to the 9th. So if I were to divide that by 2 times pi, I get 1. So whatever change is going on out here is, if you do, let's see, This right here is causing a change around the 15th decimal place. Okay. So for all intents and purposes, it's still 2 pi radians per second. So what that goes to show you is that there's so much rotational energy here that I could suck out what amounts to something like 10 times more than what the Earth uses every year in terms of power. That's what this is, about 10 times more. And I could do that for 100 years, and I would not appreciably diminish my source of energy. So I guess one way you could view this would be, if you really want green energy, you need to go find your neutron star somewhere and then develop, technology that is thousands upon thousands of years ahead of what we have right now. And then you can just, suck energy from it as it rotates. So anyway, like I said, fun little example just to show you how rotational torque is applied. Basically, it acts just like force, like I said. Remember, force times distance. Here are distances along an angle, as opposed to from point A to point B in space. All right, and so that's it. That is the last of it for chapter 10, and I'll see you in chapter 11.